Welcome back. In the previous lecture, we looked at example 56 and we found the optimal solution for this example, making use of the solver add-in in Excel. In this lecture, we are going to take example 56 a little bit further and look at sensitivity analysis. After an LP problem is solved, additional analysis of the system may be useful for many practical considerations. It will allow us to check how the parameters of the system should be changed to allow for better performance of the system, and what changes in the parameters will not affect the optimality at all. It also helps us to determine when a change in the coefficient of the objective function and a change in the right-hand side value of a constraint will affect the optimal solution. We will therefore look at the effect of changing the coefficients in my objective function and also changing the right-hand side of the constraints. What I have here on the slide is what we solved in the previous lecture for example 56, and we found that the optimal solution was for x1 0, x2 6,38 and x3 5. So we can now also create the sensitivity analysis report by clicking on Solver, and then we can add the sensitivity report by clicking under Reports on Sensitivity. And then another tab will open with the sensitivity report. And we will now look at this sensitivity report in more detail. Okay, we will first focus on the first table. The first table has relevance to the objective function. You will see that we have a column called the objective coefficients, and this column represents the contribution of each of the decision variables to the profit function. For example, we have a net profit of 1,600 for each ton of petrol sold, 2,000 for each ton of diesel, and 2,100 rands for each ton of unleaded petrol sold. Then in the column final value, we have the final values or the optimal solution for x1, x2 and x3, and that is then 0 for x1, 6,38 tons for x2 and 5 tons for x3. Next, we look at the column reduced costs. Now, for variables which are not part of the optimal solution, in this case it is x1, petrol, this index indicates how much the relevant coefficient of the objective function needs to improve so that this variable becomes part of the optimal solution. You will see that for x2 and x3 that are already part of the optimal solution, the reduced cost is equal to 0. For x1, which is not part of the final solution, the reduced cost is non-zero. Now, for petrol to be part of the final solution, the net profit from selling a ton of petrol should increase by 177,78. So we take the profit contribution of 1,600 and we add the absolute value of the reduced cost and to get the answer of 1,777,78. So if the contribution to the profit for petrol increases to this value here, then petrol will become part of the final solution. If my objective function was not a profit function, but a cost or a loss function, then to improve the objective function, we would subtract the absolute value of the reduced cost. In this case, it is a profit function, and therefore we add the absolute value of the reduced cost. And then next we will look at the two columns, allowable increase and allowable decrease. These two columns give the amount by which each objective coefficient is allowed to increase and decrease without changing the optimal solution. And if we take the objective coefficient, we add the allowable increase and we subtract the allowable decrease, we get what is called the range of optimality. And this is a range of values which the coefficient can become without changing the values of the decision variables in the optimal solution. For example, the range of optimality for diesel will be the objective coefficient, which is 2000, and then we subtract from that the allowable decrease to get the lower limit. And then we take the 2000 and we add to that the allowable increase to get the upper limit. So my range of optimality is given by 1800 for the lower limit and 2223 for the upper limit. If the objective coefficient for diesel changes within these limits, the optimal solution will remain exactly the same. But the moment when it is outside these limits, the final value for my decision variables will change and I will have to resolve my LP problem. So let's do this in Excel. First of all, I'm going to change the coefficient for x2 to a value within my range of optimality. So I'm going to change it, let's make it 1,900 rands. And we now expect that if we solve this LP problem again, that we should get the same values for x1, x2, and x3. So I solve it, and you will see that the values for x1, x2, and x3 remained the same. Okay, now I'm going to change the coefficient for x2 to a value outside the range of optimality. Let's choose a value of 1600, which falls below the lower limit of the range of optimality. And now you can see that the optimal values for x1, x2, and x3 changed. Now x1 is part of the optimal solution and x2 is no longer part of the optimal solution. Okay, then if we want to set up the range of optimality for, let's say, x3, then to get the lower limit, we will take the 2100 minus the allowable decrease of 211.11. That will give me my lower limit. And then my upper limit, you will see that the allowable increase is 10 to the power 30. So that's a very large number, and we will just set the upper limit to infinity. So that will then give us the range of optimality for x3. And in a similar fashion, for the range of optimality for x1, we will have a lower limit of minus infinity and an upper limit of 1600 plus 177.78. In the next lecture, we will then focus on the second table in my sensitivity analysis. The second table has relevance to the constraints.